There's a stretch of California that looks calm, dusty, but almost ordinary. And yet, underneath it runs one of the most dangerous fractures on Earth. People have spent decades talking about the San Andreas Fault, as if its whole story can be reduced to one phrase, the big one. One day it snaps. One day Los Angeles shakes. One day highways break, fires spread, and a disaster everyone has rehearsed in their imagination finally arrives. That is the version most people know. But what happened this year is more unsettling precisely because it does not look like disaster at all. It does not roar. It does not throw people out of bed. It does not crack walls or trigger phone alerts. Instead, it suggests that one of the world's most feared faults has been moving in a way scientists suspected for years, but had never been able to document this clearly before. Quietly, invisibly, repeatedly. And the reason that is alarming is not because it means a giant earthquake is definitely about to happen tomorrow. It is alarming because it reveals that the fault has been doing far more in the dark than we realized, and some of those silent movements appear to be linked to bursts of tiny earthquakes deep below the surface. That is the real story hiding behind the dramatic title. The San Andreas did not suddenly invent a brand new type of physics. It did something more useful and, in some ways, more disturbing. It exposed how incomplete our old picture was. A new study focused on the Parkfield section of the San Andreas Fault, used deep learning on continuous borehole strainmeter data, and identified 92 short-duration slow-slip events, including 21 that earlier human review had missed. These were not the big, violent ruptures people imagine when they hear the word earthquake. They were shallow episodes of fault slip, less than about 4 kilometers deep, unfolding so gently that they produced little to no ordinary shaking at the surface. In plain terms, the fault was slipping without announcing itself in the way people expect. And then came the part that made scientists lean in. Those silent slips were temporally correlated with increases in low-frequency earthquakes, especially in the day after the slip events, suggesting that even these gentle releases may be nudging stress around the system in ways that matter. To understand why this matters so much, you have to first understand what most people think the San Andreas is. The fault is an approximately 800-mile portion of the boundary between the Pacific Plate and the North American Plate. These plates are not colliding head-on like in a subduction zone, and they are not pulling apart like at a mid-ocean ridge. They are grinding sideways past each other in right lateral strike-slip motion. The motion is real even if it feels impossibly slow in daily life. Year after year, the plates keep trying to move, and where the fault is locked, strain accumulates. That strain can build for decades or centuries until it is released suddenly in an earthquake. But the San Andreas is not uniform from end to end. Some sections are locked and dangerous in the classic sense. Other sections creep, slipping seismically and producing many small earthquakes, but not the same kind of large ruptures. Parkfield sits in a transition zone between creeping and locked behavior, which is exactly why scientists have treated it as a natural laboratory for fault physics for decades. That transition zone setting is everything. Parkfield is not just another dot on the map. It is one of the most instrumented fault sections in the world because researchers have long believed that if you want to learn how a great plate boundary fault behaves, you watch the place where the system talks most often. Parkfield has hosted repeated moderate earthquakes in the historical record, and it lies right where the creeping central section of the San Andreas meets more strongly locked territory to the south. In other words, it is a place where both earthquake slip and a seismic slip can be studied together. Scientists buried some of the most sensitive strain instruments they have ever built there. Instruments capable of measuring tiny deformations in the rock that human beings would never feel. These tools are so delicate, they can register effects from ocean tidal loading and subtle stress changes that would be lost in ordinary seismic monitoring. Parkfield is where researchers went when they wanted to hear whispers from the fault, not just screams. For a long time, though, even hearing the whispers was not enough. One of the central frustrations in earthquake science is that having exquisite instruments does not automatically mean you can interpret everything they record. Continuous strainmeter data is messy. It contains environmental effects, instrument drift, tides, hydrologic signals, and all kinds of noise layered over the actual deformation scientists care about. Hidden inside that complexity may be tiny signatures of slow slip, but pulling them out reliably is difficult. Human experts can identify the obvious events, especially when they already know the type of pattern they are looking for. The problem is that faults do not arrange their data for our convenience. If an event is small, brief, or partly masked by other signals, it can hide in plain sight for years. That is exactly what the recent Parkfield work set out to challenge. Instead of relying only on manual review, the researchers used a multi-step deep learning workflow, including wavelet-based signal representation, a neural autoencoder, and unsupervised clustering, to search the strain records for patterns humans had not fully extracted before. What the algorithm found is the part that gives this topic its punch. 92 short-duration slow-slip events, with 21 of them absent from the earlier manual catalog. That is not a trivial refinement. That is a substantial expansion of the hidden behavior scientists can now see on this part of the fault. And the importance goes beyond the number itself. The study emphasizes that, to the researchers' knowledge, no automated slow slip detection algorithm had previously been developed solely on strain meter data in this way. So the genuinely new thing here is not that slow slip exists on Earth. Scientists have known for years that faults can slip quietly. The new thing is that this method exposed a richer population of short-duration events on the San Andreas near Parkfield than previous manual inspection had recovered, effectively revealing that the fault had been moving silently more often than we understood. The title says scientists have never seen this before, and the honest version of that claim is this. They had never been able to uncover and catalog this hidden pattern at this scale and with this method from the Parkfield strain data alone. Now, if you are hearing the phrase slow slip event and wondering why an event with the word slip in it does not simply count as a regular earthquake, here is the easiest way to think about it. In an ordinary earthquake, a patch of fault breaks fast. Slip happens abruptly. Seismic waves radiate outward and people may feel jolting ground motion. In a slow slip event, the fault still moves, but it does so much more gently and over a longer duration. The rock is still adjusting. Stress is still being redistributed, but far less of the energy is emitted as the kind of high-frequency shaking humans notice. It is the difference between snapping a ruler and slowly bending one until it creeps into a new position. Both involve motion. Both reflect stress being released. But only one gives you the sharp, violent crack. The San Andreas near Parkfield appears to be doing more of this subtle slipping than earlier catalogs showed, and that matters because subtle does not mean irrelevant. In fact, one of the most scientifically important findings in the paper is that these Parkfield events seem to follow a cubic moment duration scaling law more similar to regular earthquakes than the linear scaling traditionally associated with many larger slow slip events elsewhere. That may sound technical, but the implication is huge. It suggests that the physical boundary between fast earthquakes and slow fault slip may not be as clean as we once imagined. Instead of two entirely separate worlds, we may be looking at a continuum of fault behavior where slow and fast slip share deeper mechanics under different conditions. If that picture is right, then short-duration slow slip events are not just odd background features. They are part of the same broader language through which faults accommodate stress. That means each newly identified silent event is not merely another data point for cataloging. It is a clue about how the fault system stores, releases, and transfers stress between sections that behave very differently. Then comes the piece that makes the whole story feel more alarming. When the researchers compared the timing of the slow slip events with low-frequency earthquakes, they found a distinct temporal relationship. Low-frequency earthquake rates were higher during a slow slip event on the day it occurred, and in the 2 following days, with a particularly strong correlation on the day after the event. In simple terms, after the fault quietly slid, the surrounding system often lit up with more tiny, low-frequency seismic activity. That does not mean a hidden slip instantly triggers a catastrophic rupture. It does mean the silent motion is not isolated. It appears to perturb the fault environment around it. These quiet events may be altering local stress enough to influence the timing of nearby small seismic activity, especially shallower, low-frequency events. That is why scientists care. A slow slip event may be silent at the surface, but deep in the fault zone, it may still be part of an active conversation. And once you accept that the fault is having this silent conversation, the emotional shape of the story changes. People like clean narratives. They want faults to be either asleep or awake, either locked or rupturing, either safe for now or obviously dangerous. But real faults are more complicated than that. The San Andreas is not a single on-off switch stretched across California. It is a long, segmented, mechanically varied system with creeping sections, locked stretches, transition zones, repeating micro-earthquakes, moderate earthquakes, low-frequency activity, and now a more fully exposed population of short-duration slow slip at Parkfield. That complexity is exactly what makes the discovery feel unsettling. Not because it proves disaster is imminent, but because it reminds us that the Earth can be active in ways we barely notice until the right tools and methods finally expose the pattern. This is also where a lot of videos go wrong. They leap from any unusual tectonic finding to instant apocalypse. That is not what the science says here. The study does not claim that Parkfield's newly detected slow slip catalog means the southern San Andreas is about to rupture. It does not offer a countdown to the big one. It does not say California is doomed next week. What it says is more valuable than that. These processes may influence stress loading in adjacent locked zones and therefore matter for seismic hazard assessment. That wording is careful for a reason. Earthquake science deals in probabilities, stress interactions, and physical mechanisms, not cinematic certainty, but careful wording should not be mistaken for lack of consequence. When researchers say a hidden type of slip should be included in models of stress transfer and fault interaction, What they are really saying is that our hazard picture improves when we stop pretending the quiet motions do not matter. And that takes us back to the San Andreas as a whole. The most feared part of the system, the southern locked section, has not produced a great rupture since the 1857 Fort Tejon earthquake. North of the creeping central section, the San Andreas also has a history of major earthquakes, including the devastating 1906 San Francisco event and the 1989 Loma Prieta earthquake, on a connected segment of the broader system. USGS describes the fault north of San Juan Bautista and south of Chilam as largely locked, while the central part between these zones creeps aseismically. Parkfield lies near the handoff, where the system transitions, so when silent slip is cataloged there in greater detail than before, scientists pay attention not because Parkfield itself is the full disaster scenario, but because it is one of the best windows we have into how creeping and locked behavior communicate along a major plate boundary. That notion of communication along the fault is where the science turns from interesting to unnerving. Imagine a giant mechanical system in which one section glides, another sticks, and a third breaks abruptly when pushed too far. Even if the gliding part never produces the biggest shocks, its movements can still redistribute stress, change boundary conditions, and affect how neighboring sections load over time. Faults are not isolated cracks floating independently through rock. They are embedded in a stress field. When one part moves, however quietly, the balance shifts somewhere else. Most of the time, those shifts may be small. Most of the time, they may not matter in any dramatic way. But if your long-term goal is to understand how locked sections evolve toward major earthquakes, then ignoring slow slip dynamics would be like trying to understand a machine while refusing to study half its gears. The Parkfield study is a reminder that some of the gears we ignored were turning all along. There is also something deeply important here about methodology. The breakthrough did not come because the Earth suddenly changed its behavior in front of human eyes. It came because human analysis changed. Researchers stopped assuming that manual review and standard detection methods had already extracted the full story from the strain data. They used machine learning not as a gimmick, but as a pattern-finding tool in an environment where the signal was buried in complexity. That matters far beyond Parkfield. If one of the most studied faults in the world was hiding dozens of overlooked slow-slip events in data we already had, what else is sitting unnoticed in other archives? How many quiet deformation patterns remain unresolved on faults in California, Japan, New Zealand, or subduction zones offshore? The alarming part of this story is not only what the San Andreas did, it is what this may say about how much we have been missing elsewhere. And if you want a glimpse of why this matters for the future, look at how earthquake science is evolving. For years, the dream has been not to predict earthquakes with exact dates and times, but to understand fault behavior well enough to better estimate where stress is accumulating, how it is being released, and what precursor-like processes might matter statistically. We are still nowhere near reliable short-term earthquake prediction in the Hollywood sense, but studies like this one move the field in a more realistic and more useful direction. They sharpen the fault's behavioral record. They reveal processes operating below the threshold of ordinary awareness. They connect aseismic deformation with low-frequency seismicity. They improve source models, and they force hazard frameworks to include dynamics that are quieter than earthquakes, but potentially relevant to how dangerous segments evolve through time. So, should people be worried? The most honest answer is this. Worried is the wrong word, but indifferent would be worse. If you live in California, the San Andreas has always demanded respect. That respect does not depend on whether a new paper comes out this week or next month. The locked southern fault was already dangerous before this study. The creeping central section was already scientifically unusual before this study. What has changed is not the existence of hazard, but the resolution of our understanding. We can now see more clearly that the fault's quiet behavior is richer and more frequent than we thought. That should not produce panic. It should produce seriousness. It should push more accurate public understanding, better physical modeling, and more motivation to prepare for earthquakes as a practical matter, rather than as a distant myth. Because preparedness is where all of this stops being abstract. The public often imagines the San Andreas story begins at the moment of rupture, when the ground lurches sideways and the shaking starts. In reality, the damage story spreads through infrastructure, water systems, fires, transportation corridors, communications, hospitals, and housing. That is why California invests so heavily in retrofits, building codes, monitoring networks, and warning systems. A better grasp of fault behavior feeds into that whole ecosystem. Every time scientists learn a new way the fault stores or redistributes stress, it becomes easier to improve models, refine scenarios, and ask better questions about which sections are talking to which others. No single study ends the uncertainty, but every study that removes blind spots matters, especially on a fault where blind spots can survive for decades simply because the relevant motion is too small, too quiet, or too hidden for casual notice. What makes this discovery especially memorable is the contrast between scale and visibility. The San Andreas is gigantic, famous, and feared. Slow slip events are tiny by comparison, subtle and almost invisible. And yet, those tiny events may carry outsized importance precisely because they reveal how the fault behaves between the dramatic moments people actually remember. We tend to build our mental picture of tectonics from the big ruptures that make headlines. The Earth, on the other hand, spends most of its time in the in-between. Strain accumulates, poor pressures evolve, contexts strengthen and weaken, creep advances by fractions, slow slip migrates, low-frequency events flicker. The fault is never truly doing nothing. What the Parkfield results show is that the nothing was partly an illusion created by the limits of our own detection. And that may be the most haunting part of the entire story. The most dangerous faults on Earth are not only dangerous because of what they do in a few catastrophic seconds, they are dangerous because they are alive with processes we do not fully see, each one too quiet on its own to dominate the news, yet together capable of shaping how stress moves through the crust over years and decades. The San Andreas did something scientists had never clearly documented in this way before, and the result was not a monster leaping out of the dark. It was something almost worse for the human imagination. Proof that the dark was busy all along. What makes that especially difficult for the human mind is that slow slip attacks one of our most basic instincts about danger. We are wired to pay attention to noise, speed, and impact. If a mountain explodes, we stare. If the ground bucks, we run. If buildings fall, every camera turns. But a fault that slips millimeter by millimeter beneath ranch land without a sound does not trigger those instincts at all. It does not feel like a threat because it does not perform like one. And yet, from a scientific perspective, these quiet episodes may be far more revealing than another dramatic headline quake because they expose the mechanics of the system between the moments of catastrophe. They show the fault in motion, not only in failure. They show how stress can be released in small increments, how nearby seismicity may respond, and how sections of a plate boundary can talk to one another without the public realizing a conversation is even happening. That is why Parkfield has always fascinated researchers. It is one of the rare places where the San Andreas seems willing to reveal multiple personalities at once. On one side of the broader fault system, you have more stably creeping behavior. On another, locked segments storing strain for generations. And in between, you have a transition zone where the fault can produce moderate earthquakes, repeating micro-earthquakes, aseismic creep, and now this better resolved pattern of short-duration slow slip. In some ways, Parkfield is valuable precisely because it is not simple. It is a mechanical borderland, a place where the fault does not fit neatly into one category. And if earthquake science has learned anything over the last few decades, it is that the most important insights often come from places where the Earth refuses to behave like a clean diagram in a textbook. There is also an uncomfortable historical irony here. Humans have spent more than a century studying the San Andreas because of its capacity for spectacular destruction. The 1906 rupture near San Francisco became one of the defining earthquake disasters in U.S. history. The 1857 Fort Tejon earthquake on the southern section remains one of the great benchmark events for California hazard. Even more recent earthquakes connected to California's fault systems have shaped building codes, emergency planning, and public imagination. So for all that time, we have looked at the San Andreas mainly through the lens of rupture, through the lens of violent release, through the lens of what happens when stress wins. But the fault spends the overwhelming majority of its life not in rupture, but in preparation. And preparation has been much harder to see. That is why a paper about dozens of silent slips can matter more scientifically than another retelling of old disaster footage. It shifts attention from the final break to the hidden process leading up to it. And there's an even deeper reason scientists take that shift seriously. Earthquake hazard is not just about how much stress sits on a fault. It is about where that stress sits, how it migrates, how friction changes with depth, how fluids and rock properties influence slip, and how adjacent regions respond when one patch moves. The shallow slow slip events identified near Parkfield may not themselves be catastrophic, but they appear to be part of the system by which deformation is partitioned and transferred. That means they belong in the same physical story as the locked sections people fear most. If you leave them out, you are effectively describing the fault with missing pages. Not because the remaining pages are false, but because the sequence is incomplete. The alarming part of the new catalog is that it reveals how much more detailed the story becomes once those missing pages are restored. This is where some people ask the obvious question. If a fault can relieve stress quietly, shouldn't that be a good thing? In some cases, yes. Creep and slow slip can release part of the tectonic motion without producing destructive shaking. And that is one reason the creeping central San Andreas behaves differently from the locked southern section. But that is not the same as saying quiet slip makes a fault harmless. A slowly moving patch can coexist with a locked patch next door. A stress change that is modest in one context may matter more in another. And the study's correlation with low-frequency seismicity is exactly why this cannot be reduced to a comforting slogan like, "The fault is safely bleeding off pressure." Sometimes it may be doing that. Sometimes it may also